All right, let's get some light up there so you can see what I'm doing. Okay, circuit's right here. I'm going to bring it out and lay it on the page so you can see what I got. So there's my circuit, right? So let's walk you through what I've done here mathematically speaking. Okay, now I'm going to get a blank sheet of paper so I can lay this out and so I can draw on it and write back and forth. Okay, and I'm going to grab my calculator that's over here so you don't have to wonder what I just did calculation wise. So here's the deal. I'm going to calculate the first thing. To do this circuit, I'm going to pull this down so you can see what I'm looking at. Okay? To calc that circuit right there, I'm going to go like this. My resistor number 1 is going to be added to. Now, in this case, I have resistor number 2 plus resistor number 3. I invert that number after I add them together, and I add them to the inversion of resistor number 4. Okay, the reciprocal. Then I have to bring that back to a whole number to get it out of that parenthesis. So far, so good? Yeah. Then I'm going to add that to resistor number 5, and then I'm going to add resistor number 5 to, and I'll put a parenthesis up here, R6's inverted number plus R7's inverted number plus R8 inverted number. And then I invert that back out, and then I simply add that to R9, R10, and R11. That gives me my resistance total. In this case, my resistance total, after I added up all those numbers using these numbers right here, came out to 3,360 point, here's my numbers actually right over here. I've got them written out already. Right there, 3,360.7976. So I'm just going to write that out, 797. Got it? Actually, we'll go 4 spots. Just for accuracy's sake, because I'm calculating this. Oh my gosh. Now, once I've got that, I know I've got 2 versions of this. I've got an energy total that is 3 volts for one of them, and an energy total that is 12 volts for another one. Does that make sense? Because I got 2 versions here. So if I take my 3 volts, 3.0, and I divide it by that 3,360.7976, it's going to give me my current, okay, my intensity total at the 3 volt version. If I take the 12.0 and divide it by 3,360.7976, it's also going to give me my energy total, but that's for the 12 volt version. Okay, so I'm going to type that in right here. I take 3 and I divide it by 3,360.7976, hit my enter key. I've got this number showing up right here, 0.00. Okay, I'm going to write it out longhand. This is equal to 0.00892645. Do I have to move the paper up so you can see what I'm doing? Yeah. Okay. 64524. Well, if I write it out in proper notation, this becomes 892 point, see right there, 0.65 microamps. Okay. Now, if I do it on this other one, I'm going to take that 12 and divide it by 3,360.7976. And I get this number. It is 0.00357058098, or I'm going to move that 3 decimal places, 3.57 milliamps. At this point, I know that at R1, the current is equal to the IT. Same with the current at, I'm just going to call them I numbers now, okay? So my I at 1, 5, 9, 10, 11, and total are all the same. Are y'all clear on how I got there? So I can plug all those into my table now, if I start building it, and I can figure out what my total's got to be here, what my voltage drops are going to be at each of those. Make sense so far? Yeah, I'm confusing people, aren't I?
Yep.
Okay. It's not really meant to be that difficult. Okay. Now, I'm going to put a sheet up here on top of this and so you can see what I'm doing here. I'm going to go right here and I'm going to make a table. So my resistors are here. So there's my resistors written out. Got it? Now my resistors are the ones I showed you over here. Okay? I'm just going to get that out of the way so I can write them back on here. So my energy total that was applied is going to be 3 volts for this one. My I on this one, because it is the 3 volt version, is going to be that number I pulled up that is right there, that 892.65 microamps. Now, my resistance total I already figured out as 3360.7976. I'm just going to write it out as 798. Okay? Mathematically speaking, for this stuff, for what we're doing right now, it's not going to be a big deal. Now, here's the interesting part. My I at 11 is going to be this 892.65. My I at 10 is also going to be the 892.65. My I at 9 is also going to be 892.65. My I at 5, so if I come up here to 5, I at 5 is 892.65. And the I up here at number 1 is 892.65. And all those are microamps. Does that make sense to everybody what I've done so far?
Oh, it's so simple.
It's not meant to be difficult. It just takes effort. Okay. Now, with that done, guys and girls, what's my resistor number 11? It's a 1K ohm resistor, isn't it? Well, if I take that 1K, if I take 0.000899265 and I multiply it by 1,000, which is what 1K is, that means my energy at 11 is going to equal 892.65 millivolts. So if I take my E10 right here, got it? And I take 0.000899265 and I multiply it by, well, my resistor number 10 is a 250 ohm resistor. So I multiply that by 250. That means my voltage drop right there is going to be 223.16 millivolts here. That's all I do. I repeat that all the way on my thing. Yes, sir.
Is E11 millivolts because you times by 1.0K?
Yep, it's 1,000 K, which, yeah, that's why it's 890 millivolts right there. Okay. We all good so far on this? Well, that means number 9 is what? Number 9 is a 91 ohm resistor. If I take 91 ohms, okay, 91, and I multiply that by that 0.000899265, that means that I have 81.23 millivolts there. I can do the same thing for numbers 5 and 1 right now. Okay, because 5 is a 390 and 1 is a 470. I'll be able to figure out what my energy total is at 1, what my energy drop is at 1, and what my energy drop is at 5 really quickly here. So if I go take 0.000899265, multiply it by 470, I get 419.55 millivolts. And if I do the same thing, 0.000899265, and multiply that by 390, I get 348.13 millivolts. Now, you'll notice I've skipped my parallels, haven't I? Okay, watch this. Resistor number 6, number 7, and number 8 I'm going to do next. Because 6 is an 890 ohm resistor. 7 is a 1.8 k ohm resistor. And yeah, 7 is a 1.8 k, and number 8 is a 2.5 k ohm resistor. Okay? Now, what I have to do that, I'm going to come back over here to my other sheet, my calc sheet I was messing with. So you guys and girls can see what I'm talking about. See how I put these in a loop right here? Okay? I'm going to draw up here real quick. These right here. That is a loop, a parallel loop inside my circuit, right?
Yes.
I'm actually call it loop number 2 just for clarity's sake. This one right here, I call that loop 1. Got it? Well, right here, if I take my resistors, which look like this, can you guys see where I'm writing? I've got an 890, a 1.8K, and a 2.5K. So if I take my 890 to the -1 plus my 1.8K or 1800 plus my 2500, and then invert that back to a whole number, I'm going to get what my resistance value is in that loop because it's the same. So I'm just going to parenthesis 890 to the -1 plus 1800 to the -1 plus 2500 to the -1 close parenthesis, invert it back to a whole number. That means right here I got 480.9655338. Okay. Now, here's what the fun part, nice part is. If I've got that number right there, I can take the total current of 0.0008, that's an 8, 892.65, and multiply it by 480.9655338. And that's going to be my voltage in all 3 legs. In other words, the same voltage drop is going to occur in all 3 legs. So the voltage consumed in this is going to be the same here, here, and here. Got it? So when I type that number in and I multiply it by 0.000899265, I get a voltage drop here of, okay, 0.42. It's actually 429.33 millivolts.
3/4.
Yeah, well, it's 333.
So it's different from just
What?
So it's different from just a regular series parallel where you can subtract the total from all the other
Right.
ones. Okay.
Okay.
I can do it.
So I'm going to go back up here. See my E at 6, my E at 7, and my E at 8? I'm going to go right in this number I got over here. That's the 429.33 millivolts. 429.33 millivolts here. 429.33 millivolts here. And 429.33 millivolts here. Hold on, why?
Wait.
Where'd you get the
Oh,
first
that was
number?
91.
What number?
The number you times the resistance by.
Okay, let's back up and look at this circuit real quick.
Confusing.
All right, so when I did this part right here, this loop I called loop 1 right here. Actually, I called this loop 2. That right there. Honestly and truly, guys and girls, once I know what that resistor is, because there's nothing else in there, it's just resistors, I could turn that into a single resistor. That's a 480 ohm resistor. It would have the exact same effect on this circuit. Does that make sense? Once I know that, the voltage drop is going to be the same in all 3 legs.
Well, yeah, I got that part. Just where'd you get the first number?
What? Which is the first number?
The number I couldn't see.
The one I told you right here? The total current that's applied?
Oh, it's just the total. Okay.
It's the total current.
I can't see the numbers.
Oh, young lady, I'm worried about you now. Okay. Now, does that make sense, though, what I've done so far with this? It's just literally meant to be as simple as possible. So here's the trick, though. My I at 6 my current at 7 or the I, and my I at 8, which is my current here, all of these are going to be a function of this number multiplied by the resistance there. And if I add these three back up, it had better come back up to this 892, because what's happening is Kirchhoff's current law is being used. It's splitting the current into three legs. Part of it's going to go through 6, part of it's going through 7, part of it's going to go through 8, and it's going to come back together on the far side. Got it? So if I take that number, that one I've got, and multiply it by 890, which is my first resistor, that means I've got, okay. Oh, that's energy, isn't it? I forgot. That's energy. Energy divided by resistance. So I'm going to take my energy, I'm going to divide it by my resistance, which is 890, and I got 0.000482339. Okay, so I've got right here, it's actually 482 point, we're going to call it 4 because of where it falls, 0.4 microamps. Okay, I'm going to take that same number, this number right here, and divide it by this 1800. So I divide that by 1800. It gives me 0.00030238518. So this becomes 238 point, we're going to call it 52 microamps. Okay, and the last time I take this number right here, which is my voltage drop, and I divide it by 2500. That's going to be 0.00017, so it's 171.73 microamps. If I add these three right here back together, 6, 7, and 8, look at this. There's almost 5, 6, 7, 892. I've got, it counts for all my current. Got it? Now, I'll do the same basic thing up here with the resistor number 2, 3, 4, except for this. Okay? If I take resistors number 2, 3, and 4, well, 2 is a 560, right? What's 3?
680.
4 is 1.5.
And 4 is 1.5? Okay? So that means I'll have to figure out my energy drop at 2, my energy drop at 3, and my energy drop at 4. Now, here's the trick with it. Let's go back and look at this circuit. Whatever the total energy drop is will be absorbed, will break into these two different legs, right? So 4 will be whatever the volt energy drop is. But that energy drop will be split between 2 and 3, and because they are not the same, it will be not equally split. Okay? So as I'm looking at this, I need to do a couple things. So what we figured a minute ago, I at 2, I at 3, I at 4. I'm going to go back over here to my scratch paper that I was working on. Okay? Set this aside for a second. And I'm going to figure out that my current is what? Well, it is 0.000. Can you guys see where I'm writing? 892. Where did I get my number? It's right. It's actually that number right there, 89265. It actually goes out further than that, but that's where we're stopping. I'm going to hold on to that for a minute. That's my total current. Okay? Now, check this out. This part of the equation, I called it loop 1. If I figure out what that whole thing comes out to, it's the same thing I did here, but I'm going to do it longhand. I'm going to take that 680 plus 560, parenthesis, invert it, and then add it to that 1.5K. Isn't that what it is? I did it backwards, but additive doesn't matter. 1500 to negative 1. So I'm going to figure out right here. Okay, I'm going to go parenthesis. I'm going to go 560 plus 680, parenthesis, negative 1, plus 1500, negative 1, parenthesis, negative 1. Boom. I get 678, and we're going to round it off at 0.83 ohms in that loop. Now, if I take that number right here and multiply it by that number right there, so I take 0.000899265 and I multiply it by this number right here, which is 678.83. That's going to be my energy drop in that resistive loop. So I'm going to take that number I've got and I'm going to multiply it by 0.000899265. Well, that means I got my energy drop here is 605. We'll call it 96 because it's 959.96 millivolts. So if I come back over to this thing, resistor number 4 gets that number of 605.96 millivolts. Make sense to everybody? Now, if I've got that number there, I can then divide that number right there by 1500, can I not, to get my current in that leg? Which is 0.00043972999 or 403.97 microamps. Okay, well, this number here, these two are going to have the same current flowing through them because it has to be the same current because they're in series to each other. So if I take this number I just got and subtract it from this number, which is the total applied current, it'll tell me what the current is in those two, and then I can just do a calculation of this times this to get me that. So I'm going to do that. I'm going to take that 0.000899265 and subtract from it the answer, and I get right here a 488.68 microamps, and it's the same thing here, 488.68 microamps. At that point, I've basically solved the circuit, guys and girls. I just have to take this times this, and I'm done. 2 places. Okay, Skylar, what's your question?
So you took I4 and you subtracted 5 600.
I took I4. Okay, good answer. Good question. I took the I4, which is this, right? That 403.97 microamps. I subtracted it from the total applied current. Kirchhoff's law states what? Current law states? Well, it says that the total current entering and leaving any junction is equal to 0. Well, that means the junction right before it, right here, this junction right here, I had 403 is what I got, 403.97 microamps go through this side. So whatever's left over, that 892 microamps, has to go through this other side. So that's why I subtracted from the 892, that 403, and it tells me what's in those two. Okay. All right, guys and girls, I'm going to stop right there and let you guys and girls work out some of the rest of this happiness. Got it? You're so excited, I can tell. Where's my cursor?